Okay, let's go back in time. The year is 1905, and physics is in a bit of a jam. A huge one, actually. You see, the two great theories of the time, Newton's laws of motion and Maxwell's theory of electromagnetism, they just weren't getting along. And then, out of a patent office in Switzerland, a 26-year-old clerk is about to drop a paper that will completely tear up the rulebook on space, time, and, well, reality itself. So in this explainer, we're diving deep into the revolutionary ideas inside that very paper.
What's really cool is that Einstein doesn't open his paper with some huge, grand statement. He starts with a puzzle. He points out this really weird asymmetry in the physics of his day. He's basically saying that the explanations for how things work are clashing in a way that just doesn't make sense in the real world. And he zooms right in on one simple, elegant example to show everyone what he means.
So, what was this puzzling asymmetry he was talking about? Well, it all boiled down to a simple magnet and a conductor, like a piece of wire. The thing is, no matter how you set it up, the end result was always the same. But the official physics explanation? Yeah, that changed completely depending on what you decided was moving. Okay, so check this out. In one scenario, you move a magnet towards a wire that's just sitting there. According to the physics of the day, that moving magnet creates an electric field. That field then pushes the charges in the wire, and boom, you get a current. Simple enough, right? But now get this. What if you keep the magnet perfectly still and move the wire instead? You get the exact same current, but the explanation was totally different. Physics said there was no electric field. Instead, there was something called an electromotive force.
I mean, just think about that for a second. The relative motion between the magnet and the wire is identical in both cases, but you need two completely different physical laws to explain the same outcome, all depending on your point of view. For Einstein, this was just absurd. He believed that nature shouldn't care who's watching. The real physical law should be the same for everybody.
So how did Einstein fix this mess? Well, he didn't just try to patch up the old theories. No, he did something way more radical. He proposed two brand new postulates, basically two fundamental rules for the entire universe that would become the bedrock of his new physics.
First up, the principle of relativity. This just says that the laws of physics are the same for anyone moving at a constant speed. There is no special master frame of reference that's truly at rest in the universe. This one rule immediately cleans up that whole magnet and conductor problem. But the second rule, this is the one that really messes with your head. The constancy of the speed of light. It says that no matter how fast you're moving, towards a beam of light, away from it, whatever, you will always measure its speed to be exactly c. Now that just shatters our everyday intuition, and as we're about to see, its consequences change everything.
So once you accept those two new rules, all the dominoes start to fall. Concepts that we all take for granted just begin to crumble. And Einstein decided to start with the biggest, most fundamental one of all, the very idea of now. He asked this incredibly simple, yet profound question. I mean, we all think we know what simultaneous means, right? It's obvious. But Einstein realized that unless you have a physical way to actually define it, the whole concept is just an assumption we all make. It's baked into our brains, but not into physics.
So he came up with a rock-solid physical definition. To sync up two clocks that are far apart, say clock A and clock B, you do this. You send a light signal from A, it bounces off B, and comes back to A. The clocks are only truly synchronized if the time it took light to go from A to B is the exact same as the time it took to come back from B to A. It's brilliant because it uses his second rule, the constant, unchanging speed of light as the ultimate, impartial judge of time. And here is where reality really starts to get weird. Let's do a little thought experiment. Imagine you're standing on a train platform. A super long train is speeding past. Right at the moment the very middle of the train is directly in front of you, lightning hits the front and the back of the train. From where you're standing on the platform, the light from both strikes travels the same distance to reach your eyes, so you see them happen at the exact same instant. They're simultaneous. But what about a person sitting in the dead center of that moving train? Well, she is racing towards the light from the front strike and racing away from the light from the rear strike, so she's going to see the flash from the front first. For her, the events were absolutely not simultaneous.
This leads to a conclusion that is just mind-blowing. There is no such thing as a universal now. The very idea of two things happening at the same time is completely dependent on how you're moving. So who's right? The person on the platform or the person on the train? Well, according to Einstein, they both are. Their realities are equally real and equally valid.
Okay, so if at the same time isn't a fixed thing, what on earth does that mean for time itself? And what about space? This is where the consequences of Einstein's ideas go from just being weird to sounding like straight-up science fiction.
The logical next step is that time itself has to be relative. Einstein proved that from the perspective of a stationary observer, a moving clock literally, and I mean literally, ticks slower. He called it time dilation. He even pointed out a real-world example. A clock on the equator is moving faster than a clock at one of the poles because the Earth spins. Therefore, the clock at the equator must be running just a tiny bit slower. Time is not a constant drumbeat for the universe.
And it's not just time that gets warped. Space does too. Einstein showed that if you measure an object while it's moving past you, it will actually be shorter in its direction of travel than it was when it was sitting still. A moving sphere, if you could see it, would literally look squished into the shape of an ellipsoid. But the revolution doesn't stop there. Oh no. In the last part of his paper, Einstein takes his new rules of motion and applies them to an electron. And in doing so, he uncovers the ultimate relationship between energy, mass, and the speed limit of the universe. He came up with this new equation for kinetic energy, the energy of motion. Now I know, it looks a little complicated, but trust me, the only part you really need to focus on is in that denominator, that little bit that says the square root of 1 minus v squared over c squared. Here, v is the object's speed, and c is our old friend, the constant speed of light. So what does that little denominator do? Well, it has a truly mind-blowing effect. As your speed, v, gets closer and closer to the speed of light, c, that whole denominator gets smaller and smaller. It gets closer and closer to 0. And as you know from math class, when you divide by a number that's approaching 0, the result just blows up, heading towards infinity. The energy you need to go just a little bit faster starts to skyrocket. The implication here is just staggering. To get any object that has mass, a baseball, a spaceship, you, all the way to the speed of light, would require an infinite amount of energy. It's literally impossible. Which means c isn't just how fast light travels, it is the absolute, unbreakable speed limit for everything in the entire universe.
So, in one single paper, Einstein just took a wrecking ball to the foundations of physics. He showed us that the fixed absolute stage of space and time that we all perceive, the world that just feels so intuitive to us, is basically just a convenient illusion. In reality, space and time are tangled together, they're flexible, and they are completely relative to how you are moving.
And that leaves us with one final, profound question to think about. If Einstein showed that all these things we thought were absolute, time, space, even mass, are actually relative, then what's left? What is truly fundamental and unchanging? Well, the answer is as beautiful as his theory, the laws of physics themselves, and that one constant, that one cosmic speed limit, the speed of light.